Good, it's working. Okay, I'm good.
Thank you.
All right, we'll start. So let me just go back to where we were. Okay. All right, so fluid mechanics, week number 2, and we're trying to develop the fluid dynamic equations. And my marketing speech is that if we get the equations, we can somehow simplify them towards different problems, and that will make learning the subject much easier on the long run. And I believe that, not just saying it. Anyway, so then we had the question, we had all the question last time, what is the best way? And we mentioned different coordinate system, and we've mainly focused on the Eulerian method, where we can actually look at the control volume, and then again, we could do an integral approach or a differential approach. I developed the integral approach very quickly. I think it was fairly simple, and it's fairly good tool for one-dimensional problems. And I did some examples. I would like to continue with some of the examples and then move on to the differential formulation, which is going to be a bit more painful, but we have to get over with. Okay, so, and I think the long run, it's really worthwhile doing it. Okay, so without too much to it, okay, so this is a brief summary of what we did last time. Okay, so we picked some kind of coordinate system, and then let me get the pen. And so we said, perhaps there is a control volume, big control volume, but instead of the big control volume, we can look at the little one here, a tiny one here, and then it looks like that. And the volume is going to have a volume and a surface. And it's possible that streamlines are going like that through that. And then we try to apply some logical assumption and develop conservation rules. So the first one is conservation of mass. That was, and that basically it says that mass is not being lost. So this was describing the flux going in and out through the surface. That's the surface integral. And this part described the accumulation in. So if more goes out than comes in, then eventually the accumulation is going to be negative and the mass will be lost. Along the same lines, we developed the momentum equation. So it's the same thing, but we just added a velocity component, another one, because it's now have to multiply by the velocity. So it's mv rather just m. Here it is, we added the mq. So we didn't spend too much time because it's exactly the same thing. However, now we need to look at the forces, which this would be sigma f. So we concluded that the sigma f could be body forces. The only one that we're going to use is gravity. Again, you could use magnetics and other things. We separated the shear to pure shear, which is shear, and then to pressure. And then I explained that on a little box. Go quickly. Then, in order to simplify those, we tried to come up with a one-dimensional model, and we call that the stream tube. And we made some assumption. We said that, okay, it's steady state. At this point, there are no body forces. And also we said incompressible, although it doesn't change too much the equation, but just to make it simple. And we tried to do 1D. Now the 1D is really a good part of that simple model. And what it means is that suppose there is a hose or some tube, and the velocity comes out of it, and it has a velocity profile. But we're going to assume that the velocity is a constant across that flow field, and it's going to be actually the average velocity. We'll get back to those type of assumptions later on, but right now it's one-dimensional, so there are no changes. Then we try to come up with some simple equation from the integral representation, and we introduced this model, which is the stream tube model. So we mentioned that here's a streamline, it's going along this object, and then there's no flow normal to the surface here. Probably solid surface, could be a nacelle, could be something like that. However, the exchange of the fluid is through these surfaces. Oh, same thing I'm having. Yeah, I have to take the pen each time. If I don't take, then it jumps. Apologies, I have to get used to it. So this would be a surface when there's an exchange. In our model, we assume that the flow is going in, and there's another surface here when the flow is going out, and everything is one-dimensional. So we ended up with the momentum equation like that, and then with the continuity equation, we ended like that. Like we're saying that the flow in and out is the same because there is no accumulation, there's no time dependency. And again, this formula allows you basically to change the density. So it could be that the flow goes in and there's some heating process and then the density is different. This is still going to be valid, still good. And then if we extend that formulation into that case, we ended up with the momentum. And remember what we said, that in order to keep the control volume in place, there must be some shear force on that solid surface right here. And then the sum of those shear forces, we call them Fx. And this way, we ended up with some very simple formula, which means the force is momentum out minus momentum in, and then the pressure differences on these two surfaces, the in and out surfaces. And very, very simple formula, easy to remember. And then all the following examples are basically going to be using these two equations. That's it. And okay, so we did a bunch of examples, and I just want to continue with some of that. So let's say we have a tap, and I opened the valve, and we have a high-speed jet. And here's the area, the pressure outside of the tap is going to be equal to the atmospheric, so there's no pressure term. Exit velocity, let's say 5 meters a second. It's water, then it's 1,000 kilograms. So what is the mass flow rate? The mass flow rate, we mentioned that's equal rho UE. Okay, what did I say here? No, I think this UE is wrong. Okay, don't look at that. This is that UE here. Where's my pen? Let me get the pen. I think this is a small mistake. This thing doesn't exist. Okay, mass flow rate is rho UE, which is the first equation. Density of water, velocity of the jet, area of the jet, 10 kilograms per second. That's what's going out. Now we use the formula for the force. So if I go back to the previous page, then what we have in the force, there are no pressure terms. There's only out. So there's going to be, let me go here again. So there's going to be, this one will be there, but this doesn't exist because nothing goes in. And then this is going to be there, but actually they are the same. Therefore, this term is 0. Okay, and this one is not there because nothing is going in. So we end up with only one term. So here we go. So the force is the mass flow rate times UE, or this way, it's the same thing. Same relation, velocity square, it's 50 Newton. Okay, that's the force.
So which one do we start with?
Which one is? Okay, all right, so let me continue. I didn't hear a question. So let me get the pen. Let's see what we've done here. So in principle, we have all this in a control volume, okay? And then we have the x direction this way, okay? This way, and then we wrote down these two equations, these and this one, in that this was the basic model. So we ended up with a positive force. So now let's see what it means. It means that the shear is going to act this direction, Fx, on the control volume. Otherwise, the jet will push the whole assembly this direction. But it stays stationary, therefore we must apply a force which is a sum of all the shears. So if you hold a hose or something like that, then you must apply a force We must apply a force to keep it in place. We can ask the same question about the vertical force. So in this case, the vertical force, this is going to be the z direction, positive z. And then we write down the equation the same way. So, what I did is I just changed the area. Okay, change the area to 6. Then what happens is the velocity is this one, and then velocity is u2 is going to be slower. Okay, rho, because it's 0.06, before it was 0.002. So we increased the area 3 times. This is just what happens. I continue with the idea of the that one of the normal force. So let's see. So we can see that for going in, so we have, and going out, we have nothing. So the going in, so the out is with the positive and this is negative. So this is rho u velocity minus, I assign the minus to the area, which is actually point to the minus direction compared to the plus z that we selected, which is the normal Cartesian condition. We assume that there is no pressure in this point, which is not very good, but I assume no pressure at this point. Then if there is no pressure term, this is the only one. And then the momentum, which is trying to push the thing. So the momentum is trying to push the assembly up, but we need to apply a force to the negative direction, which is the summary of the shear, in order to hold it in place, which is that force. Okay, so this is very, very simple example. Another
Professor,
yes, is there a question? But I cannot hear you. You guys you sound broken. Question or just you talking to each other?
now?
No question, okay. So here's another one. You have a jet and it hits a plate and the plate is held in position. So the question is how much force is required to hold it in position? It is very similar to the previous problem. So how much is that force? The force. So let's see. Going in, so if I define a control volume like this, then I can see that flow going in, nothing comes out. So the flow going in is 0, the flow coming out is negative. And then there's no pressure because everything happens in the atmosphere. So there's no pressure difference between here and here. So the same thing. So this term disappears. And therefore we end up that the force must be equal to minus m dot v. So let's see what is the mass flow rate. It's going to be 2 rho, okay, which is what we said, this is water. Okay, they have 50 kilogram, oh, actually it's given, 50 kilogram. That's the mass flow rate per minute. So we have to divide it by 60. So that will be the mass flow rate per second. And then we take the velocity, which is, I took 20 meters per second. And again, I think I have a mistake. So this should be 20 meters per second. 200 meters per second doesn't make any sense. Okay, so what will be the force? It's going to be minus 16 Newton. Why it is minus? Because in our nomenclature, X is positive this way. And then the force on the plate is going to act in the minus direction. Otherwise, the plate will be blown away. Okay, so what will be the force when the plate moves at 50 kilometers per hour? So this is just to make things more complicated. So if the plate moves to this direction at 50 kilometers per hour, then I assume that the force will be less because it's just simply going away from it. So, and then there's a minus sign here. Then what will happen is the same quantity here, like here, same thing. But now the relative velocity, because this control volume is now moving at a constant speed, is going to 20 minus 50 divided by 3.6. Therefore, Fx is going to be significantly less. Okay. So again, this is a simple problem, very similar to that, but it shows that we can really use this simple one-dimensional model to get some ballpark forces in different engineering situations. Here's another one. This is actually a last year project. Somebody proposed that. And just to see how can we very quickly have a design iteration and figure out what is needed. So there was a gentleman who wanted to design a balloon that is actually not floating because of helium, but it's floating because it has a prop inside. So we suggested something with an inlet of maybe 4 centimeters, an exit of 2 centimeters. We need the difference because we want to have higher speed at the exit. Otherwise, we're not going to have any thrust. And then we looked at balloons and some assemblies. So we decided, why don't we have a complete a total weight of, let me get the red pen. Why don't we have a total weight for the system of 50 grams? And of course, the pressures are the same in and out. And now the question is how much flow rate we need, how much power and things like that. So the weight must be equal to the thrust, to the push. Pressure terms, there's no pressure term here, no pressure term here. So this is very simply the same thing. So again, if I want to continue with the story, all this thing is collected in a control volume. This would be the incoming flow, and this would be the exiting flow. And let's say if I want to use the x coordinate, then my x coordinate is going to be this direction. This is going to be positive. Therefore, the weight, which is equal to the thrust, in order to keep the balloon suspended, is going to be the exiting momentum minus the incoming momentum. Okay, so let's figure out this thing out. We have the mass flow rate, okay, but the mass flow rate is the same in and out, and therefore so these two quantities are actually equal, okay, because that must be equal to 0, the accumulation term. Okay, so therefore, we have this relation, and we can claim that the ratio between, because of the area ratio is 2 to 1, therefore the speed here, u2, is going to be twice the velocity at u1. We already have the mass flow rate, so we can figure that one out very easy, but at this point I didn't do that. So what is the thrust? The thrust is going to be, I'm just substituting to this equation, which is equal to the weight. It's going to be rho. Instead of u square, I'm going to put 2u1 square. The area is actually 1/2. And then rho u a2, which this term remains the same. And we ended up with that quantity. So now we can calculate how much is the velocity. Very simply. And here's the velocity, the weight, which is 0.5 grams times g. Density 1.2 for the air. Area is 4 times 10 minus 4. So 4 centimeters square in metric is going to be minus 4 because 1 meter has 100 centimeters. You solve that and you end up with 31 meters per second, fairly fast, And the required mass flow rate is again this formula which I have here. We can just take 1 and it comes out to 0.15 kilograms per second. So then the next thing you would do is you would look for a motor and you look for a propeller that will do the same mass flow rate. Okay, so very, very simple, just to prove that this model could be used for let me see, I have one more or two more? Yeah, I have one more. Okay, one more problem. Okay, I mentioned that, or you guys probably going to ask me, what is the most complicated problem I'm going to ask in exams and things like that. So what I presented so far is really the type of questions I expect you to understand and be able to solve. And also exams are going to be based on things like that. On top of that, we're going to have a complete one-dimensional flow chapter down the road, maybe in 2 weeks or so. So we're gonna practice this a little bit more in the near future. So I'm mentioning that because this problem is probably the most complicated you can ever get in this particular course. So what we have here, we have some kind of a duct. It's a generic cooling duct. And there's flow coming in. Well, the pressures are very, very small, so not much difference. There is a heating element. And because of the heating element, the temperature goes up, and therefore the density goes down. So the question is, what happens with the velocity? We have the areas, and we have the velocity going in. What is the velocity going out? That's the question. And we can also calculate what is the thrust, which is going to a very small number. So, okay, so let's see that one. So first of all, we use the ideal gas relation to calculate what is the density. Remember, we did the R for air is the universal. Oh, again, I apologize. My mistake is clicking before selecting the pen. Okay, selected the pen. So this one we did before the first week, and then 29 is really air, molecular weight of air. Therefore, this will be the R. Then we do the simple formula. This would be an atmosphere, which is 1.013 10 to the 5th newtons per meter square. That's in standard atmosphere. The gas constant, and let's say typical temperature, which is, what is that? We said 20 degrees C. So this is 20 degrees C. We end up 1.2 kilograms per meter cube. That's the density of the air. Density of going into the duct. Okay, so into the duct. Again, if I want to go with the story, we have a control volume is supporting the whole thing. And then we're basically comparing condition between station 1 and station 2. And it's the same model we use for the stream tube. So the mass flow rate here as before. What is that? We have the density of the air. I kind of threw away the 0.4. I forgot about that one. And velocity, we know it's going on at 5 meters a second. And then the area is going to be 0.5 meters square. Therefore, the flow in is 3 kilograms per second. Now, we need to calculate the same quantity. Of course, the mass flow rate is the same, but we need to calculate the properties. We're trying to figure out what is the velocity. So we do know that the exit velocity, exit temperature is 45 degrees C. So we just do another calculation for the density, and then 318 is 273 plus 45, which is the absolute temperature in Kelvin. And it comes out to be 1.1 kilograms per meter cube. So because of the high temperature, density goes down. Now, the first law of conservation of mass states that these two are the same. So by comparing one to the other and knowing the condition in, okay, the mass flow rate was 3. We already calculated it here, right here, this one. This is 3. And then we have to divide it by the density and then by the area at the exit. And the area is given. And we end up with an exit velocity, which is 7.73 or something like this. And it's faster because now the area is smaller and then the density is also less. And so we found out the exit velocity. Now, because the velocity going in and coming out is different, we can assume that there could be some force. And what is Fx? Okay, Fx, which we call that the shear. Pressure is the same, both sides. Something going on and going out. So what we're going to have Fx going to be equal mass flow rate and U2, which is exiting, minus mass flow rate and U1 entering. The pressure terms disappear. This is exactly what we have here because the mass flow rate is the same. And we just plug in the number. It's 8.8 Newton. Okay.
Professor, how do we know when the mass flow rate is the same going in and coming out or when it's different?
Okay, if you look at the problem, we have a continuously operating system, and there is no reason for the fluid to accumulate. If it keeps on accumulating, the pressure will build up and it's going to blow up. So it looks very logical that whatever goes in comes out at the other end, right? Because it's a continuous operating system. Do you agree to that one?
Yes, so it's safe to assume it's always the same coming in and coming out?
It has to be the same, because that we discussed that with the stream tube, that whatever goes in goes out. Otherwise, we have to leave something in. So this is a more complicated problem, because I mentioned before that one way to accumulate flow is by changing the density. And now I'm giving you a problem with change in density, and I'm telling you there is no accumulation. But accumulation would mean that flow stays in, and therefore the pressure will go up. But we stated that the pressure is the same. So this way, I'm okay in my assumption. Am I convincing you or not?
Yeah, that makes sense. Thank you.
Okay. All right. So I think at this point, I would like to end up with the examples on the integral formulation. And this is one-dimensional formulation, integral model. Quite simple. We'll get back to that. Are there any questions on that one? Because we move on to the differential, and that is going to be more painful. So you're quiet. I can assume that I can move on. Anybody say hi?
Yes.
Okay.
Hello.
Okay, that's good enough. All right. So, okay, so now we go to the, okay, you say hello. You have a very late fuse. Thank you very much. So now we're going to the hard part of the today class. And I think this is probably the most difficult, difficult class of the whole semester. And you may not understand everything. I'll make all the effort to make my explanation as clear as possible. But the overall objective of this is that you understand what are the equations and what are the components and how it was developed. Don't be afraid. I'm not going to ask you to develop components or parts or whatever of that equation, because it took hundreds of years for the Euler guys and then the Navier guys and all these, and including Newton, to figure out these equations. So there are sometimes in universities complete courses, mainly in graduate, when they do a whole semester of what I'm going to sell you in an hour or maybe less. So don't feel too bad. Okay, so, but I'm going to use some tricks that will make it easier and try to show that it's easy to understand as well. So the differential form of the fluid dynamic equation. So I want to end up with differential equations that we can eventually integrate and solve and so forth. So I already convinced you, the mouse is not good. I'm back. Let me get the pen. Otherwise, if I touch the mouse, it keeps on jumping. So I'm trying to use the same philosophy we had before. And we said there is an object. I picked up airfoil. I hope you don't mind. If for civil engineer, I can put a house here and the wind is blowing over it. But let's just have the airfoil. I'm sticking a coordinate system to that one. It's steady state, inertial frame. Everything is legal from the dynamic point of view. We put a control volume around that. And now before, what we did is we tried to somehow look at the big box, at the control volume in and out, what's happening. Now we would like to develop a function, because my argument was that in this way, like the streamlines appear to be stationary. So instead of making a very complicated time-dependent problem, we can end up with a much simpler problem. But still, we need to develop a function that will describe the velocity profile everywhere in that volume. So what we're going to do we're going to have a little box here. Let's say this little box is somewhere here. Let's see, how can I, here's the box. And then I just expand it here. And then I would like to, so this comes from here to here. And I just want to look at the flow rates and then the forces on that little element. This is kind of a fluid element. I picked up Cartesian coordinates, and also I picked a cubical element because it's much easier to explain what I'm going to explain. So conservation of mass and momentum will be done on this one. Okay, so that was the, now let's go back to this box. So I would like to look at the conservation of mass, and the philosophy is not much different than what we did before. So we're basically saying that the flow entering in the box and the flow entering out must be, if it's not the same, then there is accumulation, but this is one direction. So we need to do the same thing to three direction. If there is any difference, then there is accumulation inside. So now let's just try to look, how can we express that idea? So for example, the flow rate coming in is going to be rho v. Before we said, pen. Before we said that's going to be, and it's the y direction. So I'm going to use, again, the pen. I didn't use the pen. It's going to be rho, velocity now to the y direction is going to be v. And we use the area or S, let's say A. What is the area of that surface? Is dx dy, dz. Okay, so it's the same thing. Then I do the same thing, rho v a. But now I'm trying to see maybe something changed, maybe the velocity changed, maybe even the density changed. So let me just do something else. Let's say, not very nice. Let's say this is the y coordinate, which is parallel to this one here. And let's say this is the velocity v. And it's, let's say it's a constant before the box. This is the box. And then it comes out here. Sorry, not there. It comes out here with a higher speed. So I assume that inside the variation is linear. Therefore, the velocity outside, so this is going to be dy. Therefore, the velocity outside is going to be equal to v plus dv dy. And then the change between this line and this line is the slope times dy, which is exactly what I say here. But I also added the density, okay, because we can do the same trick for the density and then multiplied by the area, which is the area here. So that's it. So then what is the accumulation inside? The accumulation inside is the difference between this going out and coming out, okay? So that's what it is. This is the accumulation inside, okay? So we claim, that the change, okay, for the whole volume, it looks like this. So going in, coming out, times the area is this one, okay? So I'm not doing any rocket shape. I'm just changing, so this will be the change, okay? And they're very similar to what we did before. But again, I'm using the mass flow rate, not just the velocity. So now, let's see what we're gonna do. So now we need to do the same exercise to the other direction. So this will be X. Let me just get the pen first before it does disappear. So this would be X direction. This is the one that we did before. And this is the Z, the same direction. Now, what is the change inside the box? Inside the box, it's rho times volume, okay? So the change of the mass inside is d of dt of that thing. What is the volume? dx, dy, dz, that's the box, okay? And then the volume is this, and then therefore the only d acts on the density. So there must be a density change in this box if it's fixed in shape, because that's the only way that we have that one happening. So now we do the same thing. The change in the internal or the internal mass is a result of whatever guys goes in and comes out. Okay. Then that's it. That's the equation, which is the conservation of mass. And I'm back here. Then I'm trying to, I see that this term, which is the volume, appears everywhere. So I can claim that at the end of the day, I do it per volume, per unit volume. And I end up with this. All these guys are minus, okay? Because if it's a large number, then actually mass is being lost. So therefore, minus all of those. I move them to the other side. And this is the differential form of the conservation of mass. That was quite easy because it's very, very similar to what we did for the integral form. Any questions up to this point?
Is the little v velocity in this case? Because the big V is volume. Rho times script
I'm
v.
trying to answer the question. I'm trying to answer. We use velocity vector q and little u, little v, little w. Usually that is the velocity vector. Then we use, in this case, capital V as the volume. In reality, people use a little bit curly capital V to make sure that it's not going to be confusing. So to answer your question, at this point, for while we develop this equation, this is V, and I try to use capital V as volume throughout the course. It's not always possible because sometimes you have conflicting nomenclature. Are we good?
Yes, I remember that. Thank you.
Okay.
I have a question.
Yes.
You said the accumulation of mass inside the cube is due to a change in its density.
Well, what happens if I'm trying to say what is the mass inside?
Oh, okay.
The mass inside is going to be equal to rho times volume. Okay, so if there is anything in time, then I say d over dt. And then I put the d over dt over here as well. Put it around here, put it back here.
Mm-hmm.
Then I say the volume is constant. So the only poor guy that we can apply the derivative is the density.
Oh, okay. I see.
Okay?
Okay, thank you.
Well, right now I'm just trying to get the equation going, and this is complicated. Don't think it's so very simple. Why? Because if density is varying, velocity is varying, we have two different components, and then we have to, okay, let's see the next slide. I think I'm saying that on the next slide. So this is the equation I showed before, but if you really want to be correct mathematically, you can open it up. Okay, because this is a multiplication. So you open it up. So for a compressible fluid, this is the term for compressibility, because then density can change. If density is fixed, then these terms disappear, and then eventually we end up with that equation. This is the incompressible conservation of mass, which basically states that we have a box here. I'm not sure if my artistic capabilities are good, but that's what's saying flux this way. If this way is big, then everything has to come out the other direction. which was the example I did before when we tried to do the flow going one side of the pipe coming out and something on the top. Remember, we used the same principle. Okay, so that's for incompressible fluid. And it's coming out from that. Believe me, I will come back to these things when necessary, okay? All right, so you've been quiet and good audience, and I'm very pleased. So let's do the momentum equations. This is going to be a little bit, okay, so it jumped again, apologize. I mean, each time I touch the mouse without getting the pen first, it jumps. So it's going to happen more, and I'm apologizing for all these cases. So I could have done exactly the same thing which I did now. But now we have velocity square. So we're going to have 1, 2, 3 terms here. When we do the derivation, it's going to be 3 terms. And it's going to be pretty messy in terms of algebra. It's going to be pages and pages and pages. So in order to save that and try to make something rather than mathematics, try to something which is more logical, I would go to the basics. And the basics of the momentum equation is this. Change in momentum equal to sigma f. We already know that. This is from high school. So turns out that this term on the left-hand side, when developed in, it's basically acceleration, by the way. This is A, acceleration. If we develop this term, then we end up with a term which is called the material derivative, which is used in other disciplines. In other disciplines, I'm not sure if you heard about it or not, but at least you're going to learn about this. Okay, so let me focus first on the left-hand side, and then I'll focus on the right-hand side. And then once we're happy, we're going to make both equal to each other. Okay, so that's the plan. So I will focus on the material derivative because it appears that it really represents acceleration. So I go back to the original model that we had before. So let's say that we are successful and we were able to develop in that control volume functions u, v, and w, which represents everywhere the velocity. Okay, let's say it's given. So if I go to this point here, again, same problem. Let me take the plan. If I go to this point here, it will tell me right away the velocity x direction is this and the velocity z direction is this. If it's two-dimensional, there is nothing to the y. This function, these are the function. Let's say they exist. Okay, they exist. So, and of course, the velocity vector is q, and these are the components of that velocity vector. Now, let's look at a particular streamline. Let's look at this one, this streamline. And then we pick up a point here somewhere on the floor, and we say, well, what is the velocity u? We're just looking at the x component in this point. We can do x, y, and z, but let's just do x component. So the x component, oh, it's exactly this one. This is the x component. Okay, here it is. Then after a while, this particle moved here, and then the velocity could have changed. And also, there is probably some time between the two. So we can claim, based on the same equation here, that u plus delta u is going to be equal to the same function, but now we have delta x, delta y, delta z, and also the time. We have deltas, which is very logical. So assuming that this distance is very small and the time is very small, and we can have some kind of a Taylor expansion. So we just go back to good old mathematics. So left-hand side stays the same. This one is going to be equal to fx without the deltas. And then derivative of the function times delta x, derivative of function, and then second square and higher order terms and so forth. You probably know Taylor expansion. Am I safe to assume that? Somebody say it.
Yes.
Okay.
We're a bit rusty on it.
Okay, so this is from calculus course. This is just simply developing to Taylor series when this number is small. The delta U is very small, so we can approximate, and then we can go df to the third by divided by third, and then delta whatever to the third divided by 3, things like that. So we can go on. So let me go to the next one. So far, nothing dramatic. So I just recopy what we had before so we can continue. So this is the same thing. But now we're looking at some simple facts of life. Delta x, we assume that in this is a very small distance and therefore everything is constant, not changing much. So delta x is u delta t, delta y, v delta, and so forth. That's a very logical assumption. And then the first function is that, but u is also, it's the same thing as that. So if I plug in here that and that, then I can actually eliminate this term versus this term. So I'm left only on the left-hand side with delta u. And then I look at these terms. Instead of delta x, I'm going to have u delta t, v delta t, w delta, and delta. Everything is legit, so no drama here. Everything is very simple. How about we divide by delta t, because it appears everywhere. So we end up here, delta u, delta t. But if now go to delta t or delta x, which are very, very small, we take the limit, then this is really the momentary acceleration. And then the momentary acceleration is what we know before change of du dt, but it also includes these terms. And therefore, this is called the material derivative. So an acceleration in fluid is this. Am I convincing or not? Let me do one more effort to convince you. You're very quiet, or either you're sleeping or not. Let's go to the previous case. We had a tube. And the flow goes in. And then the flow comes out. But because of that, we have to apply a force F to keep it in place. But F is equal mass acceleration. So it turns out this is steady state. Everything is steady state, but this flow turns. Therefore, the particles do have an acceleration, which are these terms. Am I convincing you?
Yes.
Yes.
Any positive comments or negative or something? I feel alone here, as I was saying. I hope that you're with me, okay? And I'm not boring you too much.
Keep going.
I'm boring you, okay? Thanks for
No,
honesty.
he said keep going.
Keep going, okay. I thought I'm boring, but that's fine. On the other hand, this is very important because in other disciplines, when you get maybe to graduate studies, you're going to end up very, very similar terms, which is the material derivative. Again, this is acceleration in fluid, and we had additional terms that you've been not exposed to before. Let's stay with that, okay? So, the acceleration is this. I'm copying again. It is called the material derivative, and therefore this operator, let me be careful with this. I cannot be careful with the pen. This is the operator, basically, and it's called the material derivative. So in vector form, we can say this. It's dq. So this is the same thing, but in vector form. Okay, those that got A in vector algebra say no problem. It's exactly the same. This is the del operation. This one is the operator, the del, d over dx plus d dy plus d dz. That's the operator. So this is exactly the same thing. So we started with momentum equations, and let's remember that. So what we did so far, we said rho A acceleration. I convinced you about this. This is the acceleration. Must be equal to sigma F forces acting on that little element, cube element. So the next task is figure out what are the forces. Okay, let's do that. How are we doing? Doing okay. Okay, we go back to the little box. Okay, force terms. Yeah, I try to modify it, but I have to be in edit mode, and I'm not in edit mode. Let's forget about it. What it says, it's force terms. That's what it says here. Okay, so we had the same discussion before. So what are the forces? Let's say to the x direction is this arrow, which is probably the pressure, tau xx. This is this arrow, which is acting on the x direction, but on the z surface. Therefore, we call it tau xz. And this one, which is the tau x direction acting on the y surface. However, there are two surfaces here on the other side as well. And therefore, we need to take the difference between the two, and that is going to be the pure force. So if I want to have the correct force, actually I have to jump here. I have to take body force, okay? And I have to take the difference between the shear, let's say this is the x direction, shear, this shear xx, okay? So that's this term, the xx is the pressure. So the pressure for here and the pressure in the back. What is the difference? Is this term. This actually should be P, and later on I'm going to replace that, and there's going to be a minus sign here, if you recall. And then to the x direction acting on the y, there is this force, and then the change on the other side, the difference between the two, the net difference, this is that term. And then the net difference on the upper and the lower side, this is going to be this term. Okay, so it's not just the shear. Because of the force on the box, we're looking at the difference. So xy and tau xz are these two terms. And then the first one is actually pressure. So d tau xx is the change of the pressure versus x. All right? Agree? You are quiet.
Yeah.
I need some support.
Yes,
I don't want to feel
Agree.
we agree.
Thank you. I don't want to feel alone here. That's
Yes.
You're not alone.
I'm not alone. Okay, you're with me. Eventually, you need to know that. So you're in a bad shape if you don't listen. Okay, I'm trying to still make the explanation a bit more easy. So we had, for example, the tau in this case. So let's say the box is in between, and there is tau here and there is tau here. And then this was the official definition. However, in the case of the box, we're looking for the derivative of that. So therefore, we're going to have second derivative of velocity. And the purpose of this slide is to convince you that at the end of the day, when we're talking about forces, then we're looking at the differences between the two sides. So therefore is the derivative, that the difference with the two sides of the box. And we're going to end up with second derivative of the speed. Okay, so it's not such a dramatic thing. Now, if I go to the previous slide, okay, this one, previous slide, this, and I'm going to rewrite this one exactly the same, wrong direction. I'm going to rewrite it, then it's going to look like this. The same thing. I just used the two things, but I added the body force, the body force, I have a slide about explaining the body force. The first term, the tau xx, is actually pressure. And these are the other two sides of the cube. Okay, very, very, very simple. So we have the forces. So if I want to do it easily, then I can say that this is how we started. For example, the x direction. If I do this, then I end up with the x component. Okay. And if I do the other direction, which is y and z, this would be the three-dimensional vector representation, not vector, but differential representation of the momentum equations. That's it. Simple. But unfortunately, the previous slide shows that we would like to replace these by actually velocity component. Also, if you're a mathematics major and you're looking at the differential equation, you say, this is u, I would love to have here u instead of tau. This is different variable. So it doesn't make any sense because now I have many more variables than the three different one allowed. So, okay, so we have to go back to the drawing board and remember this term. I just put here the second derivative of velocity. Okay, so here is that one. And I just wanted to make an example of the body force, because before the body force is something mystical and all that. Now, suppose I take the previous equations, and for the body force, let me get the pen again before it jumps on me. So this is just an example about the body force. So let's say the body force is only gravity. Then the components is 0 x direction, 0 y direction, it's minus g to the vertical direction. So if I want to write down the z equations, okay, let me go back again. If I want to write down this equation for this case, this one, I'll just take this equation, and therefore here this was 0, this is going to be 0 because the body force is only minus g. I have to put here minus g, and then this equation would look like that, right here. So this just to show you how the body force comes in, and it's usually going to be very, very simple, no major problems. So one more time, I'm repeating what we had before, and this is that. So now, unfortunately, what we need to do next is to add the shear component, which are a function of the velocity. Oh, I do have the pen. Okay, so this is, we have seen it before. Let's move on. Okay, so just refresh your memory. We said that, for example, tau xx is pressure. I picked up the z, the upper surface is going to be this one minus the lower surface. We end up with this, which is the second derivative. Now, if I use this formula, I promised you not to use it too much. Oh, it runs again. I touched the mouse. I made a promise. This is the last time I'm going to show it. So I mentioned that the generic shear in a fluid, which is being also compressed, will include the compression term. And this was also the pressure, which is supposed to be here. But that's how in material mechanics they represent that. So this represents the compression. It's only at the x, y, and z direction. That's why the delta here, which is the delta function. So if I take this and I take that derivative here, because I need to have a derivative of that one, derivative of this term, and then I place it in the previous equation in a vector form. So this is the worst scenario. This is the worst scenario. We have everything included, and in vector form, so you see I took the d over dx, I. So xi could be 1 to ijk, or 1, 2, 3, or x, y, z. I put that term here, and this looks pretty complicated, okay? Because now we have a compression term. If not, then this will go away right away. And then here we're going to have the terms that we discussed earlier. It's going to look very, very similar. So it's not going to be too complicated. The big problem is this term. So by assuming the flow is incompressible, we can get rid of this term. It jumped on me again. All right, so we took this term. This is a simple one. This is the most complicated the shear can be. We plugged it in, and this is called the Navier-Stokes equation in vector form. So I just want to show a little bit more about that. And it is pretty scary, so I hope you're brave enough to continue. So if I open it up, okay, to the X, Y, Z direction, that was the vector representation. It is going to look like this. Not very user-friendly. This is how it's going to look like. Very serious partial differential equation. I mentioned the no-slip boundary condition. So the boundary condition on a solid surface is going to be velocity normal is 0, which is logical. And the velocity tangential, which is going to be, say, y and z direction, is also 0. These are typical boundary conditions. Now, this is a partial differential equations, and undergraduate students never hear about that. So please excuse me, but we jumped 2 levels, and we're presenting equations which you never studied in calculus. Then on top of everything, there's no solution to that one. So it's pretty complicated. But we do have the terms. So let me just repeat myself. This would be the acceleration, okay? And then if it's steady state, we're going to lose that, okay? And then this is body force, where we're going to only use G, which is going to be here, only that one. Pressure is pressure. Then we have this term, which eventually will disappear if this goes away, okay? And then this term is very similar to the other ones, and somehow we'll end up here, okay? So at the end of the day, we end up with something much simpler if we assume that the flow is incompressible. Let me show you that one. Let me show you, and I know we're getting close to the end of the class, so I just want to feel more comfortable. So here is if we say mu is constant, then, and viscosity is a bit constant, then we can actually represent with also incompressible. Well, not really. This is that case. So this is the same representation, and somehow we incorporated there were another term here, which was incorporated here, and this is really the compression component, okay? So it's the same thing, but with vector algebra, working a little bit and rearranging it. That's the full Navier-Stokes. If I assume incompressible, then this term is actually 0, okay? And then you end up with this equation, which is the incompressible Navier-Stokes. If you assume that the flow is inviscid, so there's no viscosity, okay? Then you end up with this one, which is the Euler equation. I have a few minutes. Let me just go back very quickly because I said something and I didn't prove it. Okay, when we discussed the continuity equation or conservation of mass, I said if its density is constant, incompressible, we end up with this relation. Where's my pen? We end up with this relation. In vector form, this is that, okay? So now I go back. So what I'm claiming here this is exactly the same thing. So then that is going to be 0. So that's why we throw away these terms, okay? And 1 minute left. I'm just opening up. So the case for Euler equations, we're going to have this, which is 0. And for the viscous incompressible flow, these are the equation. And we're going to refer to those equations mainly. So we're not going to look at the very complicated one. So this is the acceleration term. This is the pressure. Here I neglected the body forces because we're going to use only in this equation G. And these are the second derivatives, as I tried to explain earlier, of due to the shear force variation between the two sides of the box. So at the end of the day, I would love you to remember at least that particular equations. Let's see what I have here. Very brief. Okay, I run a bit faster and I have some summary. We presented the fluid equation. They of course could be represented in fluid in cylindrical or spherical. The book will have those. We're not going to use those. There is no solution for those equations. We'll have to chop components in order to be able to solve something. From the historical point of view, simple models were developed and there was no direct connection to the equation. We trying to do the opposite without reinventing the wheel. We try to show that everything comes from the same source. And basically that's what it is. I come back to that next time. And I would like to conclude the class at this point. Again, this must have been the most abstract class, most difficult. All I hope that you now know that there are Navier-Stokes equations, and these are the main fluid dynamic equations. What are the main components and what they really represent? And for the A students, I would recommend making a print of those equations and putting under the pillow at night, so maybe something will penetrate. Well, thank you very much.
Professor.
Yes, sir.
Professor, I wanted to ask, can you please put the notes up before we have the class? Is that possible? Because it would be a lot easier. I print the notes. It'd be a lot easier if I had them in front of me and I can just write on it as you're writing on it during the class.
That is a good idea.
Okay, here's my problem and we can solve it. My problem is I have the notes, but I don't know where am I going to finish. So I usually edit the notes after class. So what I can do is I can present the notes or post them, but then I will change them after the class a little bit. The change will be tiny. It's mostly beginning at the end.
That's fine. But mostly any changes, if we're paying attention, we should be able to annotate on our own notes as well, right?
Yeah, exactly. So
That is true.
basically, I didn't do there was one mistake in one of the errors, which is straightforward. I put m dot row u, m dot u, but the next relation shows that was a mistake. Okay.
It would just help us take better notes, in my opinion, me specifically. So if we can do that, that'd be great.
Let's make a deal. Before class, let's say 3 hours before class, send me an email and say, "Dear professor, please post the class notes as is."
Got it. Okay. I will send that email.
Each class, send me that,
Yep.
and I'll do it. Okay?
Okay. Perfect. Thank you.
Okay.
Professor, I have another question. For the midterm, they're on the syllabus, doesn't say like when the exam would be. Is there going to be like an estimated time when the midterm will be?
Yeah, I have only one student, I believe, though, and believe me, no problem. What we're going to do is we're going to have an email or a place or a Dropbox that you're going to send it, and those students that allowed more time will just drop it later on. So it's not a problem whatsoever. And then I only
I'm just asking like of when the exam will be, like, you know, because on the syllabus it doesn't say what day.
Will do. Okay.
Yeah.
Usually I would like to, this is very abstract. So we would like to accumulate enough material that I can ask you a question. If I want to ask you now a question, I need to ask you a question on differential formulation, and you're going to hate me and you're going to fail. And so the reason is just to continue and develop material, and hopefully month and a half into the semester, we'll be in that position. Then before that, maybe 2-3 weeks before that, I will ask you to vote on a date. And we have a, democratic way of fixing up the date, and the majority will decide what is the correct date. All right?
Got it. Sounds good. Thank you, Professor.
You're very welcome. Okay, class, thank you very much for attending, and we'll see you next time.
Thank you, Professor. Have a good weekend.
Have a good
Thank you.
Thank you.